Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so we're happy to have Ryan O'Donnell here. Ryan, years and years ago, was an intern with us in the theory group in Redmond. And then he was a postdoc with us in the theory group at Redmond. And then he escaped, or so he thought, and he went to CMU. But he's back for 3 weeks, right?
That's right, yeah.
Right, and it's not really back. It's in our new place. Okay, so he'll be talking about invariance principles in theoretical computer science.
Great. Thanks a lot, Jennifer. It's great to be here. Thanks for inviting me. Okay, so here's what I'm going to talk about in the talk. So I'm just going to start by describing a few results from the last few years that require, in computer science, that require some kind of variations on the Central Limit Theorem. And in some sense, this whole talk is basically just a giant insult to your intelligence, because I'm going to spend most of it just like proving the Central Limit Theorem, which I'm sure you've all maybe seen before. But I kind of want to show you like a different sort of version of the proof that I think is like very flexible, and I think it's like a theoretical computer science take on the proof, and show you how you can use it to get all sorts of different variations that we needed for some of these results in computer science. And then I'll have a quick open problems slide at the end. Okay, so let me just state a few results from the past few years, and I'm not really going to say specific things about them too much. I'll just go over them briefly. So almost all of them are concerned with this very basic class of Boolean functions that comes up in lots of areas in computer science, like learning and circuit complexity, and comes up in social choice. And it's just the class of linear threshold functions. So I like to write bits as plus or minus 1. So these are just functions that take n bits, and they're defined by n plus 1 real constants. And it's just the sign of this linear form over the bits. Okay? And you can see, because it's a sign, it wouldn't matter if you multiplied all these constants by the same other constant. So you can take some normalization. So we'll always assume that the sum of the squares of C1 through Cn is 1. Okay, this is also sometimes called the half space, because the set of points that make this 1 is like the intersection of a real half space in Rn with the discrete cube. Okay. It's also, yeah, nothing much happened in that slide transition. It's also common in a lot of these problems to think of the input as being uniformly random. So each of the n bits is independently plus or minus 1 with probability half. And I like to write random variables in boldface. So I don't know if you can tell that like that has become a boldface axis. But soon I'll follow the other convention that mathematicians like of writing it in capital letters, and that's clearer. Okay, so here's a result of... yes, very sophisticated. It's a great product. Here's a result from a couple years ago that I had with Rocco, learning theory. And it was about learning linear threshold functions. And we showed that you could learn them in polynomial time, which is not news. But actually, you could learn them in this like kind of weird model of learning theory called restricted focus of attention, which basically just means you have this unknown function f, and you really only get the correlation of f with each of the n coordinates. So it doesn't seem like a lot of information, but we still showed that you can learn LTFs in polynomial time. And it was like kind of a long and complicated paper. But if you take like the main parts, main theorems, main lemmas, main ideas, somehow this was like what I think of as the key. And it looks kind of familiar to if you know the Central Limit Theorem. So that if you have one of these sort of linear forms, and these are random plus or minus 1 bits, the probability that the linear form will land in some interval minus u to u is basically the same as the probability that a Gaussian will land in this interval. I also like to use capital G instead of capital Z for a Gaussian. And this is up to some error, which is big O of epsilon. And here epsilon is the maximum of these CIs. So if they're all small, then this random variable, this sum, sort of acts like a Gaussian in this sense. And that's kind of familiar to you from the Central Limit Theorem, although maybe not this precise kind of error bound. Yeah.
What do you mean learn an LTF?
So the assumption is that there's like an unknown function f, which is a linear threshold function. You don't know which one. And you sort of only get this information, and your task is to actually output a linear threshold function which is close to the original one. Yeah, the coefficients. Okay, so then another subsequent paper, we're looking at property testing of linear threshold functions. And roughly speaking, these theorem statements are not completely precise, but we showed that you can test the class of linear threshold functions with polynomially many queries. And again, it was kind of complicated, but if you like boil it all down to the central idea, like I kind of feel that this was the central fact, which is that if you look again at this sort of random variable sum of ci xi, these are plus or minus 1 bits, the expected absolute value of that is close to this magic number root 2 over pi, but it's not really a magic number. It's just the expected value of, absolute value of a Gaussian. And again, this is up to epsilon if these guys are all small. So this actually doesn't quite follow from the central limit theorem, which says that like the CDFs are close. But I'm sure if you dug into your probability textbook, you would find this result. And indeed, that's what we did. But it's a bit more complicated. Let me mention another result from this year due to Mecca and Zuckerman out of Austin. It was a derandomization result. And they gave a pseudorandom generator for the class of linear threshold functions with this very nice small seed length. And somehow the key for that result was something like the central limit theorem, but even when the xi's are not fully independent, somehow there's like a hash function and some 4wise independence going into there. I won't say exactly what, but this is definitely not something you would find in your standard probability textbook. So if you want to prove this, you really kind of have to understand and be able to sort of soup up or modify the proof of the central limit theorem. Sometimes you also need a multidimensional version. For example, if now imagine you have the random plus or minus 1 sums of vectors, ci vector in Rd. So this is sort of a vector valued random variable, and you might want to show that this is close in some sense to a d-dimensional Gaussian. I guess the usual way they formulate it is that for every convex set K, these two probabilities are close. And again, there's some error that will depend on the dimension and maybe the fact that all these vectors are short compared to some of their lengths. But this is kind of, this is also known in probability literature, but it's a bit harder to find. I remember as a grad student trying to dig out a statement like this, and it was proved first by this guy Sazonov in a Russian journal in '68. So it's kind of more complicated. But sometimes you need it. So this other paper, which I did on my visit to Microsoft in Silicon Valley, when I was visiting Parkshit, we kind of improved the randomization result to the same result, but for functions of constantly many LTFs. Maybe not the point is to go into the details of this theorem, but somehow the key for this was that you needed a de-randomized version of the multidimensional central limit theorem. So again, if you're going to do this, you kind of need to know how to prove a multidimensional central limit theorem, and it's already kind of complicated. So that's why I want to sort of tell you today my favorite way to prove this thing. The central limit theorem, which lets you add in all sorts of other features to it. And similarly, I had a paper with Blay about property testing. And I phrased the sort of key central limit type thing here a little bit different to emphasize the fact that it's sort of an invariance principle. So what we sort of needed for this paper was that, if you have like a sum of independent random variables, that's kind of close to the sum of another bunch of independent random variables, as long as they have the same means and variances. Well, you might kind of believe that, because if you know that this random variable is close to a Gaussian and this random variable is close to a Gaussian, then they should be close to each other, right? But somehow illustrates that it's more like an invariance principle in the sense that if you're taking a sum, you can put in any kind of random variable as long as they have matching means and variances, and you should kind of get out the same result. Actually, we needed a multidimensional version of this, so again, it got a bit more complicated. I'll mention one more result. This was actually something I proved when I was a postdoc here at Microsoft. It's a result that kind of gives you something nice in the theory of social choice and something nice in the theory of inapproximability. So it's one result that basically gave you these two things, that in social choice, if you look at voting schemes in two-party elections where no voter has sort of too much influence, then in some sense, we showed that majority is the voting scheme that is most robust to noise. And the inapproximability result is that if you believe the unique Ames conjecture, then it's hard to approximate max cut to within better than 0.878. Again, I won't really focus on the meaning of these theorems, but somehow the key here was like a low degree version of the central limit theorem. Yeah. Sure. I don't know. Why not? So before we were talking about linear forms over plus or minus 1 bits, but now you might look at let's say low degree polynomials. What what happens when you plug in plus or minus 1 bits versus what happens if you plug in Gaussians, and the key was to show that these kind of have the same distributions under some assumption about the polynomial. Okay, so there's all these extensions to the central limit theorem that you apparently need if you want to prove some nice results in computer science theory, and the next time you need one, it might be some kind of riff on this, some multidimensional low degree something or other. So that's why I thought it might be nice to show you like a nice flexible way to prove all of these results, and one that I think is very, I don't know, has like a computer science mindset to it, I think. Okay, so that's what I'll do next. Any questions though? No? Okay. Great. So before we get into it, let me just remind you a few things about Gaussians. Again, not to insult your intelligence, but the standard Gaussian, I'll write this random variable as g, and this is the notation n0, 1. That means that the mean is 0 and the variance is 1. Here are some like basic facts. These are not too important, but we saw this before. The expected absolute value of a Gaussian is root 2 over pi. The expected fourth moment is 3. I just write these to remind you that it's a very simple random variable. I didn't write down its PDF, but you can type it into Maple and derive these basic facts. The key facts actually we'll use about them are here in yellow. One is anti-concentration, which just says for any really small interval of width 2 epsilon, the probability a Gaussian lands there is small. It's at most O of epsilon. That just follows because the PDF of the Gaussian is uniformly bounded. This big O is even less than 1. And of course, if you take a constant plus another constant times a Gaussian, we also call that a Gaussian. And of course, its mean will be A, and its variance will be B squared. And this is really the one key fact that we use in all the central limit theorem proofs, just that the sum of independent Gaussians is Gaussian. In fact, you don't even need anything really about the PDF of a Gaussian, e to the minus x squared or whatever. You just need this fact. This is the key fact, that sum of independent Gaussians is Gaussian. Okay, any questions? Great. Okay, so let's get into it. So let's remember what the most basic, central limit theorem is, proved way back by de Moivre or whoever. I recently learned it's called the central limit theorem because I guess Levy, thought this is the most important theorem in probability theory. So central limit theorem. I just thought this had some technical meaning, but no, it has the usual meaning. Yeah. Okay, so the usual phraseology is that you have actually a sequence of random variables, x1, x2, x3, etc., and they're all independent and they have the same distribution. They're IID. Let's just assume they have mean 0 without loss of generality by subtracting a constant and common variance sigma squared. So if you add up n of them, the variance of this thing will be sigma squared times n. So divide by the standard deviation, it'll have this big thing will have mean 0 and standard deviation 1, same as the Gaussian. And the limit is that the theorem is that in some sense, as n goes to infinity, the distribution of this converges to the distribution of this. Okay, so that's a great theorem, but it's actually terrible for practical purposes in computer science for, well, 2 reasons. One reason is it's kind of annoying that these are identically distributed, but there's versions that get around that. But the thing that really makes it completely terrible is that this is a limit as n goes to infinity, and in computer science that's useless to us, right? I mean, we want to know if you want these to be epsilon close in some sense, how big does n have to be as a function of epsilon? Is polynomial in 1 over epsilon okay? Exponential, logarithmic in 1 over epsilon, what? So that is something that is no good about this, and what we really want is some kind of central limit theorem with error bounds. Okay. So in a central limit theorem with error bounds, there's no sequence. Okay, there's just n random variables. Okay, x1 through xn, and let's stay for now in the situation where they're identically distributed. Mean 0, and let's say they each have variance 1 over n, so that the sum of the variances is 1. And we want a statement that looks like this. The sum of these guys is somehow close to being Gaussianly distributed. Gaussianly is not a word. Having the Gaussian distribution. So the problem is this is not quite true, right? This is only true if you assume that the random variables xi's are not totally wacky. And I'll give you an example to illustrate that.
Is that a technical term?
That is a technical term, yeah. Here's an example of a wacky random variable, one that's 0 almost always with probability 1 minus 1 over n squared, and let's say, I guess it should be plus or minus root n with the remaining probability. So that's symmetric, so there's mean 0, and it's sort of cooked up so that the variance, which is the expected square, is, n times 1 over n squared, which is 1 over n. And if this is your random variable, then your central limit theorem, for finite n is not going to work because, I mean, by union bound, except with probably like 1 over n, all of them will be 0. So this is almost, even the whole sum is almost always 0, right? Which is definitely not true for a Gaussian. So this is just wrong. So in order to make this work, you need to assume that the random variables are somewhat nice. Okay, so there's different ways you can make that precise. Here's the simple way that I'll talk about on this slide. So what does it mean for a random variable to be like nice enough that the central limit theorem is true? So let's say you have a random variable x, its mean is 0, and by scaling, its standard deviation is some number sigma. And let's define the 3 norm of x to be the expected absolute value of x cubed to the 1/3. Okay? So it's like the third absolute moment to the power 1/3. And this is always bigger than sigma by, is that obvious? Maybe you need like Jensen's inequality or something, but it's a fact. Yes, the power mean inequality. Good. So we'll say that x, well, this definition is in quotes. We'll say that x is a nice random variable if, the third norm is not too much bigger than the standard deviation. Okay, let's say bigger by almost a constant. So here's some examples of very nice random variables, like a random bit plus or minus 1. Actually, its third norm is 1, and so is its standard deviation. So, I mean, this constant is 1 for it. For a normal, I told you that, the third norm is some 2 over pi or something. So anyway, it's like a constant times the standard deviation. These are all like nice random variables. And this is like a not nice random variable. If you do like a quick calculation, the ratio between this thing's third norm and its standard deviation is like n to the 1/6 or something. So that's not a constant. That's large. Okay, so this is not nice. Okay, so to make it, let's make it, oh, I meant to take out the quotes here. This is a real definition. Let's say x is c nice if this is bounded, if its third norm is bounded by c times its standard deviation. Okay, and most non-ridiculous random variables that you come across are relatively nice. Great. So here is like the theorem, which is like the central limit theorem with error bounds. It's called the Berry Esseen Theorem. It was proved by an American guy called Berry. I don't think proved much else in his life in 1941. And a Swedish guy, Esseen, in 1942, independently. It was World War II, so it was not so easy to communicate. So if you have x1 through xn and they're independent, let's say identically distributed for now, and the sum of the variances is 1, then this thing is epsilon close to a Gaussian, assuming, if you assume that the random variables, which are all the same, are c nice, then the error here is basically c cubed over root n. Okay, so if c is like a constant, then this is quite good. It's like 1 over root n sort of error. Okay, in other words, if you want epsilon, then n only has to be like 1 over epsilon squared. And what does close mean? Actually, we'll come back to this later, but for now we'll use like the standard definition, I guess, which is just that the CDFs are close pointwise. So for every u, the probability that y is at most u is within epsilon. That's what this means, or the probability that z is at most u. Okay, any questions about that? Actually, yeah, this is a very well-known theorem. There's like a lot of hacking on it. Even like working on this constant. The best record is due to Shevtsova in 07. It's 0.7056. Yeah, so this is good. It takes care of the issue of error bounds. There was this interesting other aspect that we didn't like, which is that it was about identically distributed random variables, so we can cancel that. This is the general case of the Berry Esseen Theorem, which actually was only proved by Esseen. I think Berry couldn't manage it. So let's assume you have n independent random variables, x1 through xn, with mean 0, and say sigma I squared is the variance of xi. And the variances sum up to 1, so that this thing has variance 1. Then this is what you get, that it's close with error c cubed times the maximum of the standard deviations. So you can actually see in the general case you need 2 things for this central limit theorem to be true. You need that the random variables are nice, they're not like wacky ones that are like almost always 0 and occasionally huge. And you need that like sort of all of the standard deviations are small. I mean, which also makes sense, right? Like if this is all you know, the sum of the variances is 1, it could be that like x1 has all the variance and the rest are just constantly 0. In which case this thing would just be the same as x1, so it could be like a random plus or minus 1 bit. So it's not going to be like this. Yeah?
Doesn't epsilon give that?
In some sense, right? Like, for example, if you assume that like all of the standard deviations are kind of close together, that would mean that they're all kind of close to 1 over root n, which would mean that this maximum is maybe small. So I mean, it decays with n in the sense that,
Okay, so you have a nominating.
yeah, I'm always fixing this normalization so that I can compare to the variance one Gaussian. But then presumably this will go down if none of these guys' variance is dominating.
Is there an example where you need the C?
Yeah, that's a good question. I'm not 100%. The question was, there's an example when you need the C cubed. Not 100% sure about that. It is a good question as whether to make like a statement where this error kind of goes to 0, you really need this level of niceness, like let's say the third moment is small. And you don't actually. The original sort of thing that's like halfway between the Central Limit Theorem and the Berry Esseen Theorem was something proved by this guy Lachmanov in 1900, and I think he used that the sort of the third moments were small. And you can, mathematicians are really into this, right? You can also just assume that like maybe the 2 plus delta moments are small.
If you take C as like the ratio of the the 2 norm, the 3 norm, I mean, don't you get it based on a unit sort of analysis?
Yeah, this has to be cubed based on, I guess.
Well, I mean, once you fix the the sigma in there, then it has to be cubed, right?
Yeah, basically, I mean, this is cubed because it's the 3 norm and
because it's whatever power it needs to be for this to be invariant under scale.
Right. But just the question of, you could also ask, do you really need all these, 3 norms to be small? You really only need the 2 plus delta norms to be small. And then like in 22, this guy Lindeberg showed that really you just need that like the contribution to the 2 norm from like stuff that's really large is not too large. Yeah, so these are like the necessary conditions here. Do you guys know this anecdote about how like Turing, when he was a junior in college at Cambridge, he like independently reproved like most of this Lindeberg stuff on like the least conditions you need for the Central Limit Theorem? Yeah. I mean, it was like 11 years later, but like in England, nobody cared about probability except for Turing, I guess. And so he proved like all this cool stuff, and then he's like, what should I do with this? I mean, none of my professors care. So he wrote a letter to like the author of this German textbook. It was actually the author is a Czech guy, explaining his results, like hoping that this guy would care. And that's funny because he wrote a letter to his mom saying like, dear mom, like I proved this cool stuff. I wrote to like the author of my textbook. I'm really worried that he might be dead though, because he was writing textbooks like 40 years ago. And it turns out the guy was dead, but eventually got put on to like people that knew probability, and he found out that like Lindeberg had proved this stuff like 13 years ago. But then at that point, like his professors were like really impressed, and they like gave him they basically said like, we'll give you a PhD for this right now, and they did. He became like a postdoc the next year. That's a funny story about the connection between the Central Limit Theorem and theoretical computer science. Okay, yeah, where were we? Yeah, this is the general case. Yeah, actually, the real way to state it is better than this. The error is actually this quantity, and actually, I want you to focus on this because we'll actually prove the stronger version with this error bound, which looks a little bit funny. It's constant times the sum of the absolute third moments of xi's. And when I first looked at that, I would say, I don't know, is that good or bad? But it's actually better than this, and I'll show you why. If you assume the xi's are c nice, it means the third norm is at most c times the standard deviation. So you get like a c cubed, like Encore said, and then sum of sigma I cubed, right? And then if you think of this as sigma I times sigma I squared, you pull out a max of the sigma I, which gives you this, and you're left with sum of sigma I squared, which is 1 by the normalization. I don't know if you caught that, but the point is that this is better, and like, please focus on this. Even though it doesn't obviously look like it means a small number, like this will be the error bound we'll try to prove. Great, so that's the statement, and now we will try to prove it. Okay, so remember the setup, independent random variables, sum of the variance is 1. I'll write S for the sum of x1 through xn, and we want to show this epsilon close to a Gaussian when epsilon is this quantity.
So you need the 3 in that.
Yeah, in the proof we're going to give it, you need the 3, yeah. Okay, any other questions? Okay, so as far as I know, there's basically 3 ways known how to prove it. There's the characteristic functions way, which is like Fourier analysis and some kind of generalization of the classical way to prove CLT, but It's complicated and I don't understand it. There's Stein's method, which is like some very magical way invented by Charles Stein in like maybe late 60s. Depends somehow heavily on like a special property of Gaussians, and I also don't understand it, so we'll skip that. And the third way is the way that I do kind of understand, which is called the replacement method. And I like it, and it's what I'll tell it to you. I really think it's like how a cryptographer would think about this proof. Not that I guess how a cryptographer would think about this proof, since the last time I really thought about cryptography was in Silvio Macaulay's class. But that's what I want to tell you about, the replacement method.
Assuming that Silvio Macaulay is a typical cryptographer, are you?
I don't know. That's my only exposure to cryptography, so maybe I have a skewed perspective. Okay, so before we get into it...
The tail of the Gaussian, I'll tell you.
Okay, good, interesting. Huh. Yeah, so before we get into it, maybe actually even what a cryptographer would think about is like, what does it really mean, this indistinguishability of distributions? So before I said, we'll say that S is epsilon close to G if, for all U, the probability S is less than U is close to probability G is less than U. But you could want different things, right? Like maybe, as we saw before, like maybe you want for each interval, S should fall into that interval with the same probability as a Gaussian. Or maybe you might want that like the absolute value of S in expectation is close to that of the absolute value of G in expectation. Well, all these can be put in one framework, which is that of, imagine you have a test function, T, a test. I think it's a function from the reals to the reals. And you might hope that sort of S and G are indistinguishable to that test function in expectation. Okay? And, all of these three facts are of this form. For example, if, your test function T is the indicator of this half-infinite interval, that's like saying this fact. Or if T is the indicator of an interval, that's like saying this fact. If T is the absolute value function, that's like saying these guys are close. So we're going to try and prove something like this. Okay? Now, for what test functions should we try to prove it? Well, we can't hope to prove it for all test functions, because that would be like saying that S and G are perfectly indistinguishable, which is not true. Okay? So we have to pick some nice class. And in the replacement method, we're going to choose T to be the class of all smooth T, meaning like all, infinitely differentiable T. Well, for now, we'll choose that, which is a nice class, although you might think it's a weird choice, right? Because like all these, things that we cared about here are not, most of them aren't even continuous, right? So none of these are smooth. These are the things we want, but I told you we're going to prove it for smooth T. Well, it's nice to prove it for smooth T, and then like if you want this, you just do like a hack, okay? So you like, if you want this for this test function T, you like make a smooth version that like almost looks like it, use this result here, and then like use a hack that says, a Gaussian's probably not going to fall in this tiny interval anyway. Okay, so I'm mostly going to skip that and just focus on proving this indistinguishability for a smooth T. Does that make sense? Okay. Great. So where have we gotten to? Again, we got S, the sum of the xi's, we got G, and we want to try to show that for a smooth T, expected value of T of S is close to expected value of T of G, where again, this is our error bound. Okay. So we're now sort of set up. Now there's only really two interesting things that happen in the proof. So here's the first time that something kind of interesting happens. The way I like to think about this statement is that somebody has sort of unfortunately oversimplified the statement. Okay? They should have not oversimplified it. They should have stated it like this, that you want, this is important, I guess this yellow means it's important. They should have said that you want to show that S is close to G, where you think of G as the sum of G1 through Gn, where Gi are independent Gaussians, and Gi has mean 0 and variance the same as Xi. Okay? And that's the same statement, right? Because we know sum of Gaussians is Gaussian, so if you sum up these guys, you'll get a Gaussian with variance 1. But when you look at it like this, now somehow it looks nicer, like you're comparing sum of xi's to the sum of gi's. And these guys have matching, well, they both have mean 0 and they have matching variances. In fact, once you write it like this, you may as well say, hey, there's nothing special about Gaussians. Maybe I can just use any. Oh, oops. Damn it. You should, now you might think to use the hybrid argument. Now that it's so set up like this, you have x's and then you have g's. In fact, I was going to say, it's really, you can prove just instead an invariance principle that has nothing to do with Gaussians. It just says if you have any x's that are independent, y's that are independent, they have mean 0 and their variances are like the same. if I call the sum of the x's sx and the sum of the y's sy, you might try to show that for any smooth t, expected value of t applied to s sub x is close to the expected value of t applied to s sub y. Okay. With this error bound, it's like basically the sum of the absolute third moments of the xi's and the yi's. Okay, so this is actually, even better than this invariance principle version is even better than this, Gaussian version. If you have this, then you can just take the y's to be Gaussians, and then luckily you get this like simplification that the sum of Gaussians is Gaussian.
You have one and say, well, if they're both like.
Yeah, you're right. But actually, this is somehow nicer because if you go to eventually if you go to, for example, instead of summing x's, maybe some low degree polynomial of the x's, then with the invariance you can say that the low degree polynomial of the x's is close to the low degree polynomial of the y's, but there's no one distribution like Gaussian that they're both close to somehow. Anyway, any other questions? Okay, so now it seems like a lot of setup, but now this is what we'll try to prove.
For this other and the thing about Gaussians is that the sum of the Gaussian is a Gaussian. The sum of the general thing is not your general thing, right?
Yeah.
So, but maybe you're not going to use the fact that the sum of the Gaussians is Gaussian.
Well, the only place we'll use it is right here. So I mean, we'll sort of show this, that the sum of anything is close to the sum of any other thing that has matching means and variances. And then in particular, you could take the second thing to be Gaussians. And then finally, you could also observe that sum of Gaussians is Gaussian.
But you're saying, why go that far? Right?
Yeah, I
You
mean.
could do it even without that. Okay.
Yeah.
Okay.
Okay, good. Any other questions?
Is there like a universal smooth function?
A universal, sorry?
Smooth function, for which if it works, it will work for all smooth functions.
Not as far as I know. Just say that, Dan and Jelani also have all sorts of work on this kind of stuff. So if you know the answer, just feel free to chip in. But not really. I mean, at least if you have t to be maybe a smooth version of an indicator, that you can get a lot of stuff. Well, I'm not sure. Not really.
Do you need some extra assumptions here on t though? That it's
Yeah. Eventually, we'll impose an extra assumption on t. I'm kind of hiding that for now. Okay, so right, as I said, now really let's try to start proving things. So we're going to try and do it with, a hybrid argument or the replacement method. So we're looking at s of x, which is the sum of the x's, versus s of y, which is the sum of the y's. Everything, all two n-guys are independent. Think of it that way, and they have this pairwise matching means. Well, actually, both means are 0 and matching variances. Okay, so the hybrid method says you should, introduce some random variables like partially y's and partially x's. So we'll define z sub I to be the random variable, which is, the first I things you add up are y's, and the last ones you add up are x's. Okay. So by definition, sx is z0, that you have no y's, and the last one, sy, is zn. That's when you have no, you have no x's. Okay. And so we're trying to show that this is small. This is the expected value of t of, let's say, z0 minus expected value of t zn. So by telescoping and triangle inequality, it's enough to bound the sum of the absolute value of the differences between the adjacent zi's. Okay? Is that fine? Oh, okay. So yeah, just pushing some of that stuff up here. And in fact, that's convenient, because if you remember, the error-bound epsilon we were eventually shooting for was big O of the sum of the xi third moments cubed and yi third moments cubed. And we have a sum here, so I mean, it's just enough to show that term by term, this difference is at most the O of the third absolute moments of the xi and yi's added up. Okay, so just to remind you, here's z, and this is our goal. Okay, so let's look a little bit more carefully at what zi minus 1 and zi are, because they're quite similar, right? Let's also just quickly use linearity of expectation to make this thing. This is a small step, but it's important. Expected value of the difference of t zi minus 1 and t zi. Okay, so what is tzi minus 1 and tzi? Well, actually, I mean, these are almost the same thing, right? You take the first I minus 1 y's, and like the last guys from I plus 1 through n are x's. That's this what I've called u here. And then in zi minus 1, you stick in xi, and in zi, you stick in yi. Okay? So just making u this everything except the ith bit, we can express this like this. And an important thing to note, we'll definitely use it, is that u, xi, and yi are all independent. Okay. Again, stop me if you have a question. Yeah, so now to remind you, just our goal again is to show this, that in absolute value, the expected value of the difference between tu plus xi and tu plus yi is at most this thing. And now maybe by staring at this, you might get the only one other idea in the proof. I mean, what are we going to do here? We have t, which is a smooth function, applied to u, which is some like crazy number, potentially a large number, because you're adding up like n minus 1 things, plus xi, which is actually a lot smaller than u, because it's just one thing. So you have a smooth function at like some, arbitrary point plus something small. You might think to use Taylor's theorem to like approximate that. So that's what we'll do. We're actually going to sort of apply, like, imagine like u, xi, and yi all get chosen in this expectation. So now like these are just numbers. We'll then kind of like apply Taylor's theorem like sort of for every choice of u, xi, and yi. Okay. Pardon me? No, but as Adam suggested, there will eventually be one assumption about t. That makes sense? I mean, u is like a random number, and we're going to apply it to each choice of u in xi and yi. So again, this is what we're trying to show. So, let's apply Taylor's theorem to t of u plus xi. So here it is. I'll take it out to degree 3. So it's t of u plus sort of the first correction is t prime at u times xi. Second correction is half plus t double prime u xi squared. And then you get this error term. It's like 1/6 t triple prime u star times xi cubed, where like, if you remember from calculus class, u star is like some mystery point between u and u plus xi. Okay, so it's some point like near u, but it's not the same as u. Okay, and well, same is true of t of u plus yi. It's tu, t prime u times yi, and similarly. And then you get a different mystery point, u double star here. So for each choice of like u, xi, and yi, this is the truth. And well, now we're going to subtract them, right? So when you subtract them, some good stuff happens. So this stuff cancels. Then you get t prime u times xi minus yi. You get a half t double prime u xi squared minus yi squared. And you get the difference of these two things, which for now I'll just write as error term. Okay. And then here's the key step. What happens next? You get this thing for each choice of u, xi, and yi, and then you take the expectation of it. So what happens? This is the magical part. See, when you take the expectation of this, well, you can do it term by linearity of expectation. So first we'll do the expectation of this. Well, this t prime u is very mysterious because u is complicated and t prime we really know nothing about. But the one thing we do know, it's said here, is that u is independent of xi and yi. So the expected value of this is the same as the expected value of this times the expected value of this. And that's great because expected value of this, who knows, but, well, expected value of xi and yi are both 0. So this cancels and this is 0. So this all goes away. Something similar happens here. Again, by independence, you can say the expected value of this piece is expected value of this times the expected value of this. And by virtue of the fact that xi has the same variance as yi, well, it's the same because they have mean zeros, the second moments being the same. Again, this also cancels. Yes. Yeah. Sometimes you can go further if you want and save a bit. Like for example, if yi is a Gaussian and xi is like a random bit, then actually the third moments are both 0. So you can actually go to the one more step, and that'll save you a little power in the end. Yeah. But in general, you can just stop here. And that's why we stopped at 3. Yeah, so then we get that this thing that we're trying to bound is just exactly equal to the expected value of the error term. Is that clear? So we're actually kind of almost, we're sort of all done now.
The 3 norm, does that mean expectation?
Yeah, this means this thing is just the expected absolute value of xi cubed. Yeah, so it's hard to do this all in one slide, so I'll flick back and forth, because now all we really need to understand is the expected value of this error term. So we'll move the absolute values inside even. It's at most the expected value, the absolute value of the error term. And then, yeah, I claim it's at most this, because the absolute value of the error term is just the absolute value of the difference of these. Okay, I'll keep the 1/6. I'll just say that, this third derivative of t at these mystery points is just bounded by like the maximum value of the third derivative of t anywhere. Okay, so I'm going to have to make an assumption about that in a second. And then what's left over is, maybe again with the triangle inequality, expected xi absolute value cubed plus expected yi absolute value cubed. Okay, which actually is just this. By definition, that's this piece. So we're totally done as long as the maximum third derivative of t at any point is at most a constant. So let's just assume that that's true, and then we're done. So what we managed to show, and I'm kind of almost done now, is that this is a variant of the Berry Esseen Theorem. It's actually, in some ways, it's more powerful than the original Berry Esseen Theorem. In some ways, it's weaker. It's a variant. So if you have any test function, actually, it really only needs to be C3. It doesn't have to be smooth, but any smooth t where the third derivative is uniformly bounded by some m. And whenever you have x1 through xn and y1 through yn independent, and they have matching means and variances, then s of x sort of fools t with respect to s of y. The error is m times epsilon, where this is m and this is epsilon.
C2 with Lipschitz continuous derivative, second derivative would be enough, right?
Maybe C3 with Lipschitz. C2? Yeah. What does C2 mean?
Well, it's twice differential.
It should be at least 3 times differential. Well, actually, I don't even know.
The second derivative is Lipschitz continuous.
That could be. It's the computer science perspective. I unfortunately don't know the freshman calculus. I need to get the minimal conditions. Yeah. So I kind of want to stop here, although, in terms of proving this, although you're probably curious about how to get the original statement, which is this one, that if you only care about closeness in this sense, that the sum of the x's less than u has the same probability as the sum of as g. Like I said before, with this error, you can try to get this from the variant by the hack, right? You cook up a smooth function like this, where this has this interval is with delta, and you try and say it's similar to this. Actually, you lose a bit, because if you cook this up, the third derivative of this thing will be like 1 over delta cubed. Anyway, sorry to say, actually, if you take the variant Berry Esseen and this hack, you get the usual Berry Esseen, except instead of getting the right error O of epsilon, you get O of epsilon to the 1/4. But, we're computer scientists, so what's a polynomial factor between friends? Yeah, that's it. So, how am I doing on time?
Doing awesome.
Great. I thought you guys were supposed to ask a lot of questions. They offered me 2 balls of water, and I said, why would I want 2 balls of water? And they said, well, they ask a lot of questions. You might get tired of talking. But luckily, I only took 1. Okay, so the reason I actually want to show you this instead of the other versions, like the characteristic functions version, and sorry, yeah, yeah, sure, yeah. Phew, thank gosh.
You assume that the third norm of the xi's, you assume that it's very, very small. I'm trying to understand what this restriction means.
You don't assume that it's small per se.
Well, if I want to get a meaningful result, I should accept some of these norms.
Yeah, if you want to get a meaningful result, then you want this whole sum to be small.
Right.
Like, for example, if they're just, let's say, plus or minus 1 bits times 1 over root n. You need to times 1 over root n so that the sum of the variances is 1.
I'm trying to see, is this normalization factor a real issue or not? That's what I'm trying to understand. So we normalized everything, like, okay, let's just normalize. But is this coming into play now?
Oh, no. No, because
If you had said like each guy had variance 1 or something, then you would actually have it divided by n somewhere on the right-hand side, right?
If I said that each guy had variance 1,
it would look more natural because there would be like epsilon is the sum divided by n. Or there would be like divided by
well, it's a bit weird because then you would have to put a Gaussian with you have to put Gaussian with variance n here.
Yeah, no, but I'm just saying then you would have divided by n. Right? There is a divided by n.
But then your test function, the third derivative of it would change.
Yeah, but I mean here you still have
I'm getting slightly muddled, but I would say that like I can assure you that like this is like sort of fully general and like has the correct scaling in the sense that like if you have a bunch of x1 through xn with let's say mean 0, but they don't have the sum of the variances as something else, then you'll get the best possible thing and the correct thing just by like dividing them all by the same constant to make this true.
So let's think each one of them has sigma equals 1 or something like that.
Okay.
And then you'll take the sum divided by n. Like that's the usual kind of, when you think about it, you look at the sum, you divide it by n, and you say it's close to a Gaussian or whatever.
Yeah.
I mean, so the point is the following. I mean, the point is that we're going to get an error that looks like the sum of the cubes, which is going to be like n, times the size of the third derivative of our function. So if we want that to be small, we need the third derivative to be smaller than 1 over n, which means we need the scale of the function to be bigger than cubed root of n, basically. So if our test function changes on a scale slower than cubed root of n, we'll be okay. But on the other hand, since we've got n guys of variance 1, like we're comparing this to a Gaussian of standard deviation square root of n.
Yeah. So if you don't want to actually look into the proof, I mean, you could state this more generally. Skip this condition. You should say that you should put s here. You should put Gaussian with the appropriate variance here, and then the error will be this thing: sum of the third norms cubed divided by the sum of the variances all to the power 3/2, which seems a bit weird, but it's the correct scaling so that you get an error which is invariant when you, let's say, multiply these all by a constant. So actually you most usually see that if you like just look in your textbook for the Berry Esseen Theorem. They skip this and they say the error is this thing divided by the sum of the variances all to the 3/2. But yeah.
So is epsilon going to 0 with n if I had your example of the plus minus 1 is probability 1 over square root of n?
If let's say the xi's are all like plus or minus 1 over square root n with probability half each, then this is satisfied. And then the expected absolute third moment is like basically 1 over root n cubed, which is 1 over n to the 3/2. And then if you sum that up, you're summing up n things so that you get 1 over root n in the end, which is good because that's a small number. It's 1 over root n. It's kind of just like, if you have like a bunch of numbers and you normalize them so the sum of the squares is 1, to say that like they're all small is sort of roughly equivalent to say that the sum of the cubes is small. Because if they're all small, then the sum of the cubes is small, and you can do this trick of factoring out the max.
So would allow you maybe some of the sigma i's to be a little larger.
Yeah.
Not too many of them.
Yeah. So
not too much larger. I can't choose a few of them of order 1 otherwise.
Exactly. So actually, the way I commonly use this in all these results about LTFs, with all these results about linear threshold functions, xi is like a number ci times a random plus or minus 1 bit. So it's just random plus or minus ci. And you normalize it so the sum of ci squares is 1. And then instead of using sum of ci cubes, I just say that epsilon is at most the maximum of the ci. So just as you say, the error, if it's like sum of ci xi, it's just like the maximum of the ci. So the error is like subconstant if and only if all of the coefficients are subconstant. Okay, so as I said, the reason I like this proof is, you can use it to like roll your own version of like some, modified version of the central limit theorem for whatever task you want.
Are you using bold small letters for random variables and bold big letters for vectors?
No. Anything that's bold is random variable, big or small, and it has a little arrow above it if it's a vector.
Oh, I don't see the vector.
Yeah, there are no vectors here. It's like I used words.
Oh, and the next line, it's not vectors anymore.
Right. But as I said, if you want a vector valued version of this, vector valued random variables, it's no problem. Just use the multidimensional Taylor theorem. Really the proof is identical. It's very trivial to extend to multidimensional case, at least to get the variant version. The de-randomized version is also quite easy. Mainly the main trick you use for this is that if you have a bunch of independent, if you have a bunch of nice random variables, and they're even 3-wise independent, then their sum is also basically equally nice. This is an absolute constant. That's pretty easy to prove, and that's the key for this. And similarly, for the higher degree version, basically the only extra thing you need is that if you have a bunch of independent C-nice random variables and Q is a degree D polynomial, then Q applied to these guys is somewhat nice still. It's O of C to the D nice. Exponential dependence on D. This is also easy to prove by induction if you set it up the right way. Yeah?
What sort of randomized thing are we trying to prove?
There's various things you could try to prove. You have some stuff. I was thinking about Mecha Zuckerman. They need more than this, but like this is one ingredient that you need. This is like when they're trying to show that like if you first like divide the x1 through xn into like blocks using like some pairwise hash function into like t blocks, and then within the block, instead of choosing the random variables independently, you choose them, let's say, 3-wise independently, and you only put independence across the blocks, then it's kind of, you only need like t, factor t for independence, but you still get error that's like 1 over root t. So it lets you trade off the amount of independence you need with the error you achieve. Great, so I won't show it to you, but just assure you that you can use this method to prove reasonable versions of all these more complicated central limit theorems.
The second part.
I don't know. I know that Lindeberg in 22 and Bergstrom in 46 proved the Berry Esseen Theorem using the method of compositions, which I believe means a more complicated version of this. I don't know who the first one to say, hey, you can do like a simple version and get something almost as good is. I learned it from Krzysztof Oleszkiewicz, but it's definitely like it's in like textbooks, for example. Some textbooks at least.
Question.
Yeah.
So the second point, when we're looking at the sum, we don't really want to prove that it's O of C nice, we want to prove it's Gaussian, right? Is it that the bound is replaced, C in the bound is replaced by a constant times C? Or?
Yeah, so if you want to prove the sort of the corollary of Berry Esseen that I stated when you have C-nice random variables, where the error, instead of being the sum of the third moments, it's like C cubed over the maximum standard deviation. Right. The point is you can still get that bound in this de-randomized version with C replaced by O of C.
Right.
Okay. So I just have 2 more slides. I threw out some open problems. One is, this replacement method, which I like, and it's quite simple. As I said, it gets you a variant Berry Esseen, which is more, in some ways, incomparable to the original version. I actually don't know how to get the original version without losing this power of 1/4. I would love to see it. As I said, I know you can do it with this method of compositions, which is like some super complicated extension of the replacement method. So I'm wondering if you can do it with like a non-super complicated method. I think the method of compositions is, it's like replacement, but like you have to do like a big special case in the hybrid argument. Like first you have to do a special case when I is 1, and then you have to do a special case when I is between 2 and a constant, and between a constant and n over 2, and like n over 2 and n, and you have to do like different tricks for each of these 4 regimes. So it's a real mess, and it ends up being like, to me, like no more simple than these other methods that I don't understand. So I would like to see a way to get just the usual Berry Esseen with this simple kind of method. I didn't really talk about these extensions too much, but in the vector value case, it's a very interesting open question to get In the vector valued case, what does it mean to say that two vector valued random variables are close? One thing you could do is say, let's say for all convex sets K, the probability that the first guy lands in K should be close to the probability that the second guy lands in K. In D dimensions, you can get a theorem like this, and there's some dependence on D, which is known to be somewhere between log D to the 5/2 and D to the 1/4. So it can't be independent of D. But you can imagine, instead of taking convex sets as your test, some other kind of sets. For example, if you take the test sets to be balls, then actually you can make the bound independent of D. So somehow I feel like the correct dependence on the test set K should be in terms of their Gaussian surface area. But I won't really define what that is. But there's some interesting open questions there. And actually, Harsha, Clivens, and Mecca have like a nice paper in the last stock that does something like this. For the higher degree case, one question is whether you can improve this exponential dependence on the degree D in some cases. And another problem is to find more applications. Yeah, that's it. So I'll end with this advertisement. Do you like LTFs and PTFs? Do you like probability and geometry? Then just right before Fox, there'll be a workshop at the Princeton Interactability Center entitled Analysis and Geometry of Boolean Threshold Functions. So we got Diaco Nicholas and Kane and Mecca and Rubenfeld and Servideo and Shvilka and Vampala and more to come. So if you're interested, you should also come. And here's the URL. OK, thanks. Questions? Yeah.
I'm curious about the hack. It's not at all obvious to me that you can immediately go from these smooth things to...
Yeah, I can explain the hack. It takes about 1 minute.
Oh, sorry.
What's that? No, it's fine. All right. I'll explain it to you afterwards then. Yeah. There's a hack.
What is it?
Let me see if I go back to the hack. Yeah. So, so first step, you would cook up a function that looks like this. This interval has width delta, and it's you do some kind of construction, and the third moment is bounded by 1 over delta. The third derivative is bounded by 1 over delta cubed. Kind of makes sense, right? The first derivative is going to be like 1 over delta, clearly, and the other ones. And then you say, what's the probability that s of x is less than u? Or let's say, what's the probability that g is less than u? It's basically the expected value of t of g with this function, maybe plus delta, because there's some delta, proportional to delta chance that the Gaussian will land in here. So you get the original error epsilon plus this delta. And actually, the original error is the m times epsilon, where m is the maximum of the third derivative. So the overall error you get is 1 over delta cubed, which is the maximum third derivative, times epsilon, plus delta. You get 1 error from the Berry Esseen and 1 error from this, there's some chance that you'll land in here. So you get delta plus 1 over delta cubed times epsilon. And then you balance these by taking delta to be epsilon to the 1/4. You get epsilon to the 1/4 plus epsilon to the 1/4. Actually, there's one additional trick, but forget that.
You need to do one more thing.
Yeah, you need to know one more trick because, well, here we use the fact that for a Gaussian, the probability that the difference between these two things is basically the probability it lands in here, which is delta. Now, you think you would also need to do the same thing for this sum, but how do you do that?
Yeah.
It's not obvious. So you use another trick.
By a bump function.
Let's
use the same lemma to show that
That's the way you guys do it. The way I do it is you do this twice. You say the probability that s of x is less than u is sandwiched between expected value of t of s when t is this thing shifted to the left by delta and this thing shifted to the right by delta. So you make one smooth version which is always above the indicator and one smooth version that's always below. I don't know if you can keep this all in your head, but then you do the Berry Esseen theorem twice and get that this thing is sandwiched between the t for Gaussians, and then those themselves are close because Gaussians are anti-concentrated. So they're all close. Yeah, so you do have to use an extra fact about Gaussians here. And that's why, way back here, I think that something to do with the Gaussian surface area comes up, because we're really using the fact that the boundary, you're saying something like the Gaussian boundary of this step function. So in higher dimensions, something similar. That's, you noticed the thing I was trying to hide there. Let's try. Any other questions?
Okay,
Okay,
thanks.
thanks.
Brian.